In the vast, silent expanse between the stars, light can travel for thousands of years without ever touching a world. But sometimes, something crosses that void. Something small, ancient, and carrying the chemical clues of a completely different solar system. When the object we now call 3IATLAS entered our neighborhood, it brought with it a mystery astronomers never saw coming. Its path through space clearly marked it as an interstellar visitor, a traveler from beyond our sun's domain. But its chemistry, revealed by the powerful infrared vision of the James Webb Space Telescope, would completely change our ideas about what other worlds might be made of. This is the story of a discovery that stunned even the most experienced comet scientists. A cloud of gas, a coma, surrounding 3IATLAS that was overwhelmingly dominated by carbon dioxide. Using JWST's near-infrared spectrograph, a team of researchers found that the gas escaping this object contained about 7 times more CO2 than water vapor. A ratio like that is almost unheard of in our own solar system. It challenges everything we thought we knew about how ices form and are preserved on small bodies in distant planetary nurseries. And in the silent language of light, it whispers about the conditions around other stars. Conditions that might be wildly different from those that shaped our own home. To understand this story, let's start with what it even means to detect gas around a faint interstellar comet. Comets, whether they're from here or from far away, are basically dirty snowballs. As they get closer to a star, the sunlight warms their surface, and the frozen gases turn directly into vapor. This vapor expands outward, creating a temporary atmosphere called a coma. For comets in our solar system, water is almost always the main ingredient of this gas cloud. Sure, there's CO2, sometimes a lot of it, but it rarely outnumbers water. But the light from 3IATLAS told a completely different story. Before we dive into the chemistry, let's talk about the incredible instrument that made this possible. JWST's NIRSpec is designed to break down infrared light into its component wavelengths, almost like a prism. Different molecules absorb and emit light at very specific wavelengths, creating unique signatures. In the infrared, carbon dioxide reveals itself with a strong, unmistakable signal around 4.3 microns. Water vapor also has its own distinct spectral fingerprints. By comparing how strong these signals are, astronomers can figure out how much of each gas is streaming off the comet's nucleus. In the case of 3IATLAS, the result was loud and clear, a coma absolutely packed with carbon dioxide. Now, you might be wondering if this strange ratio is just a fluke, some kind of instrumental error. But the data from JWST is solid. The CO2 signal is strong, clear, and definitely coming from the comet. The water signal is there, but it's much, much weaker. This gives us that incredible ratio. For every 1 molecule of water escaping, there are about 8 molecules of carbon dioxide. We've never seen anything quite like this among the comets that orbit Jupiter, and it's extremely rare even for the comets that come from the farthest, coldest reaches of our own solar system, the Oort cloud. The spectrum is telling us that this visitor is chemically unique. A ratio like this demands an explanation. To appreciate why it's so significant, we need to think about how comets are made. Their cores are a mix of frozen gases, mostly water, but also CO2, carbon monoxide, methane, and ammonia, all stuck together with dust and organic materials. The amounts of each depend on the temperature where the comet formed in its original protoplanetary disk. Water freezes at relatively warmer temperatures. CO2 needs colder conditions, farther from the star. So, the chemical layers inside a comet are like a frozen record of the temperature history of its birthplace. In our solar system, water is king because our disk's temperature gradient made it easy for water to freeze and stick around. But interstellar objects are time capsules from alien disks. Their makeup reflects conditions that could be dramatically different from those around our young sun. The CO2-rich coma of 3IATLAS suggests it formed in a place where carbon ices were much more common than water, or where water was somehow removed. Another idea is that it was bombarded by cosmic rays during its long journey through interstellar space. This radiation could have stripped away the surface water ice, leaving behind the more protected CO2 layer underneath. One fascinating possibility is that 3IATLAS formed in the coldest, outermost regions of its home system's disk. In these frigid zones, water might have been less available to freeze, but CO₂ could have condensed in huge quantities. Observations of other young star systems show that CO₂ ice can be plentiful in these outer regions. Another scenario is that the comet started with plenty of water, but lost it over time. Cosmic rays can slowly erode and change surface materials over millions or billions of years. Lab experiments show that water ice can be depleted by radiation, while CO₂ ice is more resilient. With 3IATLAS, we're looking at a blend of mysteries. It has a chemical composition unlike any typical comet, and it's only the third confirmed interstellar object we've ever seen. The first, Oumuamua, showed no gas at all, which left scientists baffled. The second, 2I's Borisov, looked a lot like a normal comet from our own Oort cloud. Now 3IATLAS gives us something completely new, a carbon-dominated object that expands our understanding of cometary diversity. This raises a key question. What does a CO₂-rich gas cloud tell us about the inside of an interstellar comet? Comets often have layers, with the most volatile materials buried deeper. As the comet heats up, these layers start to vaporize from the inside out. If 3IATLAS had its surface water stripped away by cosmic rays, then the CO₂ we're seeing might be from a deeper layer that's just now being exposed to the sun's warmth. Or maybe the entire object is just genuinely packed with more CO₂ than water, pointing to a formation environment far colder than anything in our early solar system. The fact that so much CO₂ is escaping also tells us something about the comet's structure. Cometary activity depends on how easily heat can travel inward. A porous, loosely packed object allows heat to penetrate deeper, triggering the release of volatiles from below the surface. Interstellar objects might have had violent histories, getting flung out of their home systems with great force. This could have fractured their surfaces, allowing the sun's heat to reach deeper layers today. In a way, the CO₂ cloud might be telling a story not just of the comet's birth, but of the chaotic event that sent it on its journey. JWST's amazing capabilities allow astronomers to see these details, even though the object is incredibly faint. 3IATLAS is much smaller and dimmer than the previous interstellar comet Borisov, making it a real challenge to observe. But the powerful CO₂ emission at 4.3 microns shines brightly in the infrared, making it a great tracer even when the comet's core is too small to see. The fact that the spectrum is so dominated by CO₂ means most of the sun's energy is going into vaporizing carbon dioxide, not water. This discovery has implications that go far beyond just one object. It reshapes our view of how diverse interstellar planetesimals, the building blocks of planets, can be. Comets form from icy dust grains in a protoplanetary disk. Their chemistry is a product of temperature, radiation, pressure, and the materials available. If one interstellar visitor releases no gas, another looks normal, and a third is a CO₂ factory, it means the variety of protoplanetary disks out there must be truly immense. We can compare 3IATLAS to our models of how disks form. In our own solar nebula, CO₂ ice was expected to form efficiently beyond a certain point called the CO₂ snowline, which is farther out than the water snowline. Observations of disks around other young stars confirm that CO₂ can be a major ice component. But even then, water is usually more abundant because it freezes more easily. For CO₂ to dominate like it does in 3IATLAS, its home disk must have been a very different environment, either one with much less water or one with an extraordinary amount of carbon dioxide. Maybe 3IATLAS formed around a star with a much cooler disk, or one with a different kind of radiation from a nearby massive star. The level of ionization in a disk also affects how volatile ices form and are destroyed. For example, CO₂ can form on dust grains when carbon monoxide reacts with other molecules created by ultraviolet light, so a disk with more UV radiation might produce more CO₂ ice, but that same radiation can also destroy it. The final result depends on a delicate balance. All these factors contribute to the incredible diversity we see in exoplanet systems. And now, with objects like 3IATLAS, we're not just inferring that diversity, we're sampling it directly. As these interstellar travelers pass through our solar system, they give us brief glimpses into the chemistry of alien planetary nurseries. JWST's detection of a CO₂-dominated coma from 3IATLAS is one of. It suggests that our own solar system's comets, as varied as they are, might just be a small sample of what's really out there. There could be planetary systems where the rules are completely different, where carbon dioxide, not water, is the main component of icy, celestial bodies. Think about what this means for how planets form. Comets are like cosmic delivery trucks, bringing water, organic molecules, and other vital ingredients to newly forming worlds. If the mix of carbon dioxide, carbon monoxide, and water varies wildly from one star system to another, then the pathways to creating a habitable planet must also be incredibly diverse. A system where comets are dominated by CO₂ might deliver a very different set of atmospheric ingredients to its planets. This could change everything, from their greenhouse effects and surface chemistry to the very chemical pathways that might lead to life. We know water is essential for life as we know it, but the availability of carbon can determine how complex a young world's chemistry can become. With its massive output of carbon dioxide, 3IATLAS hints at a home system where carbon-rich ices were everywhere, potentially allowing for chemical evolution unlike anything we've seen in our own cosmic neighborhood. In our solar system, carbon dioxide starts to turn into gas or sublimate beyond the orbit of Mars, where it's still too cold for water ice to melt. Many of our comets gently wake up at these distances, spouting jets of CO₂ before water takes over as they get closer to the sun. But with 3IATLAS, the opposite seems to be happening. Water remains a minor player, even as the comet heats up. This strange reversal suggests one of two things. Either there wasn't much water ice in its outer layers to begin with, or its long journey through interstellar space has permanently altered its structure, diminishing its water supply. That journey through the void is incredibly harsh. Objects like 3IATLAS are exposed to the full force of cosmic rays, with no solar wind to shield them. Over millions of years, this constant radiation bombardment can transform the surface, creating a tough, organic crust and depleting any water ice near the top. Lab experiments have shown that this process can break molecular bonds, drive off hydrogen, and change the surface chemistry in ways that affect how it behaves when heated. A heavily processed crust could trap or even generate more CO₂, while allowing water to escape or transform. If that crust was then cracked open when the comet was violently ejected from its home system, the newly exposed layers might show a distribution of materials that is anything but pristine. Even so, none of these explanations alone fully capture what the James Webb Space Telescope detected. The ratio of carbon dioxide to water isn't just unusual, it's extreme. It suggests that CO₂ isn't just some leftover layer, but a fundamental building block of the comet itself. If that's true, this object might have come from a part of its protoplanetary disk where water ice just never formed efficiently. This could be due to low pressure, a lack of dust grains for ice to form on, or fluctuating temperatures caused by a variable young star. Some young stars go through periods of dramatic brightness changes, which can shift the snow lines, the distances where different materials freeze back and forth. A rapidly moving CO₂ snowline could have created pockets in the disk that were super-enriched with carbon dioxide ice, leading to the formation of objects just like 3IATLAS. There's another layer to this story. In the cold, dark clouds of interstellar space where stars are born, carbon dioxide can be both a product and a reactant in ice chemistry. Carbon monoxide can freeze onto dust grains and, with a little help from UV radiation, react to form CO₂, especially when water is around. If the molecular cloud that gave birth to 3IATLAS's star system was unusually rich in carbon monoxide, then CO₂ could have become abundant very early on. This ancient reservoir of carbon dioxide might have been incorporated into the disk and persisted, shaping the small bodies that formed there. We actually observe these kinds of chemical variations in star-forming regions across the galaxy. So the CO₂ signature in 3IATLAS might be a clue that traces its history not just back to its home system, but to the very cloud of gas and dust from which its star was born. When the JWST captured the spectrum of 3IATLAS, astronomers weren't just looking at a faraway comet. They were analyzing material that was forged light years away, in a completely different cosmic environment. Spectroscopy is like a time machine. It turns faint, distant points of light into chemical archives. That specific signature of carbon dioxide reads like a journal entry, written billions of years ago on icy grains orbiting a star we may never even see. Every molecule escaping from the comet's nucleus is a survivor of that incredible history, finally set free by sunlight after a journey that may have lasted longer than all of human civilization. To put this discovery into perspective, let's compare it to the other interstellar visitor we've studied up close, 2I Borisov. Borisov had a more familiar mix of water, carbon monoxide, and carbon dioxide. Its dust properties also looked a lot like our own solar system's comets. This suggests it came from a place that was chemically quite similar to our own cosmic backyard. 3IATLAS, on the other hand, is a complete outlier. If Borisov represents a class of interstellar objects similar to the comets in our Oort cloud, then 3IATLAS may belong to an entirely new and different category. The galaxy could be filled with types of planetesimals we haven't even begun to imagine. Some astronomers believe that interstellar objects are the leftovers from the violent, chaotic early days of planet formation. As giant planets migrate and rearrange themselves, their gravitational tug-of-war can scatter trillions of comets and other small bodies out into deep space. In our own solar system, the formation and movement of Jupiter is thought to have ejected countless icy bodies into the interstellar medium. If 3IATLAS came from a system with even more extreme planetary migrations, its ejection could have been incredibly dramatic. Such events can literally fracture these objects, restructuring their interiors and exposing deep reservoirs of volatile materials that wouldn't normally see the light of day. If that's what happened, the extraordinary amount of CO2 we see might not just be about its formation chemistry, but also the physical damage it sustained upon being kicked out of its home. These fractures could have opened up direct pathways for buried carbon dioxide to sublimate and escape efficiently. Meanwhile, any water ice deeper inside might have remained shielded, leaving CO2 as the main gas pouring out once sunlight reached those exposed zones. Even in our own comets, we see activity concentrated in jets erupting from specific vents. If the vents on 3IATLAS primarily tap into CO2-rich layers, the entire coma we observe would be shaped by this single dominant material. So, the JWST observations force us to think more broadly about the nature of these small bodies traveling between the stars. Interstellar comets are different from our own, not just because of where they come from, but because they've endured far more extreme conditions. Constant exposure to high-energy particles, long periods spent at temperatures just a few degrees above absolute zero, and the absence of any significant gravitational pull all shape their internal evolution. When an object like this finally encounters a star, its reaction can be completely different from what we'd expect based on our local comets. This is what makes 3IATLAS so incredibly valuable. Its chemical output gives us a real-world test for our models of how small interstellar bodies evolve. The strong dominance of CO2 supports theories that predict significant water loss from cosmic ray exposure. At the same time, the fact that CO2 survived suggests it either formed on the spot through radiation chemistry or was shielded deep inside. These findings help us refine our understanding of ice chemistry in extreme radiation environments, which is relevant not only for interstellar objects, but also for bodies in our own outer solar system, like the trans-Neptunian objects. The presence of so much CO2 also has physical implications for the comet's nucleus. Since CO2 turns to gas at warmer temperatures than water, deep reservoirs of it could cause internal pressure to build up as the comet heats up. This could create cavities, new vents, or even trigger sudden outbursts. Although we didn't see any dramatic outbursts during the JWST observation, the strong activity suggests such events are possible. If one were to happen, it could expose even deeper layers, giving us a chance to study the comet's internal structure indirectly. The implications of this discovery ripple out even further into the study of exoplanetary system architecture. If a planetary system is producing CO2-dominated comets, it must have very specific temperature and pressure conditions in its outer disk. That system might go on to form planets with chemical inventories vastly different from Earth's. If water is less abundant in its building blocks, terrestrial planets might struggle to form large oceans. At the same time, an abundance of CO₂ could lead to thick, carbon-rich atmospheres, creating powerful greenhouse effects that completely alter a planet's climate stability. By studying interstellar comets like 3IATLAS, we are starting to trace the chemical diversity of worlds we haven't even discovered yet. In this way, interstellar comets are messengers from unseen solar systems. Each one is a sample from a protoplanetary disk that may have vanished long ago. Each one holds clues about the physics and chemistry near a star whose light may never reach us. With the JWST, we finally have the ability to read these messages with unprecedented precision. The detection of a CO₂-dominated coma isn't just a chemical curiosity. It's a new data point in the emerging science of comparative planetesimal studies, a field where objects from across the galaxy become touchstones for understanding the vast diversity of how planetary systems form and evolve. As 3IATLAS travels away from our Sun, its activity will fade. The carbon dioxide will freeze once more as the temperatures drop, and the comet will return to its dormant state. Before long, it will slip back into the darkness, escaping our solar system at thousands of kilometers per hour. Its trajectory will carry it back into interstellar space, joining countless other icy wanderers. For billions of years, it may travel undisturbed, passing silently through the cosmos, awaiting a chance encounter with another star. The vastness of space means such encounters are rare, but for the few that do happen, they carry with them the chemical stories of their origins. The significance of this discovery will last long after 3IATLAS has faded from our view. By revealing that carbon dioxide can be the dominant driver of an interstellar comet's activity, this observation expands our entire understanding of small body chemistry. It challenges the assumption that water-rich comets are the universal standard. It suggests that the processes shaping planetary systems can differ radically across the galaxy. And it provides a crucial foundation for future missions. It's a profound question, and we're standing right on the threshold of being able to answer it. In the meantime, the detection of 3IATLAS's unique makeup is already a landmark achievement. Think about it. A single spectrum, captured at just the right moment as this visitor from another star system passed by, has given us an unprecedented glimpse into a world formed under conditions completely alien to our own. Its chemistry carries the ghostly signature of a star whose properties we can only infer, a planetary disk whose structure we will never map, and a birthplace now so dimmed by time and distance that we can never hope to see it. And yet, through the elegant physics of infrared light, we can read the story of this distant origin with remarkable clarity. It's like cosmic archaeology. The light from 3IATLAS, filtered through its coma, is a message in a bottle that has traveled for millions, perhaps billions of years. And with JWST, we finally have the key to decipher that message. It's a testament to human ingenuity that we can reach across such vast expanses of space and time to understand the story of a lone, wandering comet. Observing 3IATLAS with the JWST is a powerful reminder of a fundamental truth. Our galaxy is not some static, unchanging painting. It's a dynamic, living ecosystem of stars, planets, and countless small bodies, all in constant, swirling motion. Comets born around other stars are continuously being cast out into the interstellar void. Some are ejected during the violent, chaotic dance of migrating planets, while others are flung outwards during the dramatic birth of giant worlds. Each and every one of these icy travelers carries a pristine chemical record of the physical conditions in its home system. They are time capsules from other solar systems. As we intercept these cosmic messengers, we gain perspectives that are simply impossible to obtain by looking at distant exoplanets alone. We can see exoplanets, we can measure their size and mass, but we can't touch them. Interstellar comets, however, bring a physical sample right to our doorstep. They provide the ground truth, the raw data, for our models of planet formation. They don't just tell us how planets grow, they reveal how the very building blocks of those planets differ from one star system to the next, all across the galaxy. And so, as this chapter of 3IATLAS's journey through our solar system comes to a close, it's worth taking a moment to reflect on the incredible capability that made this discovery possible. The James Webb Space Telescope, with its extraordinary ability to split the faintest beams of light into their constituent molecular fingerprints, is unveiling secrets that have been hidden in the dark for billions of years. The detection of a coma dominated by carbon dioxide is one of those secrets, a profound insight carved from the darkness by a telescope orbiting 1,000,000 miles from Earth, gazing into a part of the electromagnetic spectrum that is completely blocked by our own atmosphere. JWST's location and its sensitivity to infrared light are what make it so revolutionary. It operates far from the interfering heat and light of Earth, and it can see the specific wavelengths where molecules like carbon dioxide, methane, and water ice vibrate and absorb light. This is how it reads their chemical signatures. For 3IATLAS, this meant we could finally see the true nature of its coma, a nature that was invisible to telescopes on the ground. It's a breathtaking technological feat, a new eye on the universe that is showing us things we never even knew to look for. In the grand scheme of things, 3IATLAS reminds us that the universe is filled with worlds we will never visit, star systems we will never see directly, and stars that will never rise in our night sky. It's a humbling thought. The sheer scale of the cosmos is almost beyond our comprehension. Yet through the power of science, their stories can still reach us. A tiny fragment of ice, liberated from its parent star and cast into the deep, unending night, drifts across the cosmos for eons until, by pure chance, it happens to cross paths with our sun. For a brief, fleeting moment it warms up. It awakens from its long slumber, and its frozen gases burst forth into a brilliant coma. And in that light, it tells us its story. It tells us where it came from. Then, just as quickly, it recedes back into the cold and the dark, its tale told, continuing its lonely journey through the galaxy. It's a poetic and beautiful dance of physics and chance, and we were here to witness it. The detection of 3IATLAS's carbon dioxide-rich coma is so much more than just another astronomical result published in a scientific journal. It is a powerful symbol of the vast, incredible diversity of planetary systems that must exist out there. It's a testament to the power of our modern telescopes, which are becoming ever more capable of probing the universe's deepest mysteries. And it's a profound reminder that even the smallest, most unassuming objects can carry the grandest of truths. As 3IATLAS fades back into the interstellar distance, its spectral imprint remains with us. It's a permanent record, stored in our archives. And within that faint signature of light lies an epic story. The story of a distant world, of a frigid birthplace, of a violent ejection from its home, a long and lonely journey through the void, and a brief, fiery encounter with our sun. And within that story lies the promise of everything that future interstellar visitors will teach us. About our galaxy, about the nature of planetary systems, and ultimately, about our own place in the cosmos. The cosmos is filled with wanderers. Some are rogue stars, drifting between the spiral arms of the galaxy. Some are entire planets, cast out from their systems during periods of chaotic migration. And some are like 3IATLAS, tiny, fragile, icy messengers carrying the pristine chemistry of distant alien worlds across the interstellar gulf. Through this one messenger, we have glimpsed a tantalizing possibility, that the building blocks of planets beyond our sun are far more diverse, far stranger, and far more varied than our own. In that diversity, now revealed for the first time through the power of infrared light, will serve as a crucial guidepost as we continue our quest to explore the origins of planetary systems all across our galaxy. This is the ultimate legacy of the JWST's detection of a carbon dioxide-dominated coma around 3IATLAS. It is a discovery born from distant, ancient light. It is a revelation carved from a signal so faint it's almost undetectable. It is a deep insight into a world we will never see, carried across the darkness by a traveler older than human civilization itself. What an incredible time to be alive, to witness these messages from the stars finally being read. Thank you so much for watching. If you're as fascinated by these cosmic mysteries as I am, be sure to subscribe and join us as we continue to explore the wonders of the universe. See you next time.